Okay, let's do some classic limits. Alright, this is if we plug this in, we're gonna get some 0 over 0. In last video, we talked about L'Hopital's rule. So let's apply L'Hopital. So let's take the derivative of the top, d dx, derivative of the bottom, d dx. Alright, you're gonna get cosine, because it's a derivative of sine, over 1, take the limit as x equal to 0. We can just plug the 0 now. Cosine of 0 is 1, so that's 1 over 1. That is 1, right? Absolutely not. What? Come on. And if you're confused, yes, it is 1, but there's an issue with this approach to solve it. And let me explain it to you. Say I want to find the derivative of sine x, because we need to prove that the derivative of sine x is cosine x, so we can accurately apply L'Hopital's. So let's do that. Let's prove it, right? Let's take the limit as h approaches 0 of sine of x plus h. Well, h plus x is the same thing, but x plus h minus sine of x all over h. This is your definition of derivative. This is what you use to prove derivatives. Okay, so I see a sum inside the sign, so let's break that apart. So it's going to be the limit as h approaches 0. I see two sine x's. Let's factor that out and split the fractions. So we can use the rule of two limits that equal that have. So if I have limit of this function plus this function, I can break them apart and can take the limit of the first function and the second function. That's just your limit rules. So let's do that. Let's factor out the cosine h while I'm doing that. So let me take the limit as h approaches 0. Over h. Now, these cosine of x and this sine of x have nothing to do with the actual limit because they're in a different variable. They're actually just a constant in the h word. So let's factor that out of the limit. We're not factoring each other out, we're just putting that outside the limit. Yeah, that's a better choice of words. Sine of x. Okay, you see a problem now? We're back here. If I ask you to prove this and you take L'Hopital's, you're going to be back at proving cosine is the derivative of sine, and you're going to be back here and we're going in a circle. This is what it's called, circular reasoning, okay? You can't use a concept that uses to prove another concept that uses that same concept to prove this concept. So if I use concept A to prove concept B, I cannot do that if I use concept B to prove concept A. That is called circular reasoning because we're going in a circle. So, now if you're wondering how do we know that the limit as x approaches 0 of sine of x over x equals 1, let me teach you. Okay, we're back. So now I have this diagram we're going to consider, and we're going to set up an inequality. So we can use the squeeze theorem. If you don't know what the squeeze theorem is, let this be an explanation too. So, one thing I do notice is I have three areas to consider. The area of the triangle ABC, so let's write that down. Area of triangle ABC. And we're going to say we also have an area of this circle sector with radius 1. So let's write that, and we know this is going to be greater than this triangle. So let's say that the area of the triangle is going to be smaller or equal to the area of sector AD, right? And this third triangle here, EBD, which is also going to be greater than the area of the sector. So this is the area of triangle EBD. Okay, so now let's make up some observations. So we know the radius of the circle is 1. We know that this side is 1. This entire side, the length of BD is 1. So, and if say, let's call this angle theta. right? We know that this side over here, because of SOHCAHTOA, is sine theta, right? Because this is going to be usually 1 times the radius times sine theta, because it's the opposite side, and the radius is 1, so sine theta. Likewise, what about this? Likewise, this side is a little trickier, but remember that this length of BD over here is 1, and we know that tangent is opposite over adjacent. So the opposite side must be the adjacent side times tangent, and the adjacent side is just 1. Then guess what? DE is also tangent theta. It's not also, but it is tangent theta. The sector, well, the sector, we can use the formula area of sector equals 1/2 theta r squared, right? R squared is 1, theta is just theta, whatever theta could be, and this 1/2 is just 1/2. Okay, so now that we have a thing, we know that the area of the sector is just theta over 2. So let's write this down in the equality now. Now that we have actual, somewhat numerical representations of each area. Area of ABC is this side times the base, which is just cosine x, cosine theta. I should probably write that down. Completely forgot about that one, I'm so sorry. Cosine theta, because this is going to be the radius times the adjacent side, right? Which is theta, cosine theta. See what I'm talking about? So let's write this down. So we have sine of theta, cosine of theta is smaller than or equal to theta over 2, like we just discussed. Smaller than or equal to 1/2 tangent theta, but this side is also 1, so it's just tan theta over 2. I also realized I forgot about the 1/2 over here. I was testing you. I didn't forget. Anyways, let's simplify this so we can look for our limit. Because remember, we're looking for the limit as theta approaches 0 of sine theta over theta I. That's our goal. So let's use this in order to find our goal. Okay, so I see 2's on the bottom. I don't like that. Let's multiply 2 so we can get that out of there. And let's rewrite tangent theta as sine over cosine. So let's do sine theta, cosine theta. Since we multiplied 2 on both sides, we're not going to rewrite that. 2 is smaller than or equal to theta, which is smaller than or equal to sine over cosine. Sine theta over cosine theta. Okay, since we're trying to get this sine theta over theta, one thing I do want is a sine near that theta, and I want it to not be multiplied with, I want it to be divided by. So let's do this. Let's not divide actually, let's multiply each side by cosecant theta, which, if you don't know, this is just 1 over sine theta. So let's multiply cosecant theta on all sides. Cosecant theta and sine theta go to 1. Same likewise over here. So we're left with cosine theta is smaller than or equal to theta over sine, which is smaller than or equal to 1 over cosine. So let's do that. Cosine of theta is smaller than or equal to theta over sine, which is smaller than or equal to 1 over cosine. Okay, we're almost there. We just want to flip this. So let's flip it, right? We can do that. It's called raising the entire thing to the negative first power. So when we flip it, we also gotta make sure we switch our inequality signs, because 1 over a million is a really small number. You see that logic? You're basically going on the opposite spectrum. So 1 over cosine theta is smaller than or equal to sine theta over cosine theta, smaller than or equal to cosine theta. Right? We flipped everything. So now we have our actual thing that we want to do. We have the exact same thing. We rewrite this over here so that you can see it. Right? So now we have this. Now we need to remember that we're trying to take a limit. We're not trying to set up some inequalities with sine and cosine. We're trying to find a limit. So let's take the limit as theta approaches 0 of the entire expression. Okay, 1 over cosine of 0 is 1, because cosine of 0 is 1. So 1 is smaller than or equal to whatever we're trying to find here. We don't know. That's our goal. Cosine theta, which is theta is 1, theta is 0. Theta is 0. Cosine of 0 is 1. Okay, well, now we found our limit. Now we got an inequality in terms of a limit. And guess what? I'll use some simple logic over here. If the limit is between 1 and 1, what is the limit? It's 1. It's like saying it is definitely a cat, but it's also definitely a cat. It's a cat, right? If it's between 1 and 1, the only number it could be is 1. If you don't believe me, give me any number between 1 and 1 that it could be. You can't. So that means that these are all equal to each other. Therefore, by the squeeze theorem, because we squeezed it, I prefer to call it the sandwich theorem because we sandwiched it. So, by the squeeze theorem, the limit as theta approaches 0 of sine of theta over theta has to be equal to 1. And we are done.